Hello, and thank you for joining us. Today's webinar is the MVX7100 Workstation, a new automation tool for high-precision isotope ratio analysis. Our presenter today is Pete Winship, Technical Product Manager for Teledyne CETAC. If you have any questions, please feel free to email them directly, and Pete will respond to you individually. Okay, now I'm going to turn it over to our presenter, Pete Winship.
Well, hello everybody, and thank you for joining. Apologies for our technical difficulties. And thank you for the kind introduction. So my name is Pete Winship. I'm a technical product manager over at Teledyne CETAC Technologies. I am responsible for the ASX7000 series automation, and one of the systems that's part of that group of automation is the MVX7100 microliter workstation, which I'll be discussing today. And I'll be discussing that with respect to isotope ratio analysis and how we would use this system for high precision work. So I will make a start. Right. So first of all, the MVX7100 microliter workstation. So just an image here of what the system is. So I wanted to start this webinar with this photograph. I'll be referring back to this just to walk you through it as we proceed. Now I do have an agenda that I'll work through quickly for this webinar, but where I wanted to start today was it's really sort of a concept, really, just to keep referring back to. So what I want to refer back to through this webinar is just the idea of, with respect to ICPMS sample introduction, what I want to come back to with the MVX system is how we can tailor the sample introduction process to the sample volume that you have. And that sample volume will vary across every laboratory's different requirements. That will be whichever kind of application that you're working with, the kind of analytes that people are interested in, etc. So we're going to be just talking about tailoring that sample introduction process with specific sample volumes, but also specific sample introduction flow rates. And the idea behind this is to generate the maximum or best data that you can from the sample that you have, and for low volumes, overcome some of the challenges which are posed by a minimal amount of materials that you might have. And that might be a minimal amount of a solid mass, which is then put into a volume of sample matrix, or it might be in a liquid form already. So this is where I'd like to come back to through this presentation. So the agenda for today, I just wanted to walk through these items. So first of all, I just wanted to talk about the idea of challenging and unchallenging sample volumes in ICPMS, i.e. high and low. Then talk about the conventional, just briefly about the conventional sample introduction approaches, which will be common to a lot of ICPMS instrumentation and laboratories. After that, the MVX7100 microliter workstation itself, and then a specific example in geological analysis, and then how with multicollector ICPMS, and how conventional sample introduction plays into that, as well as the MVX7100 system. And then I'll wrap up and conclude from there. So challenging and unchallenging sample volumes, high and low. So let's start there. And I wanted to start here as sort of like a backdrop to what we were going to say. So basically, as everybody who runs ICPMS instrumentation will be aware, the availability of a sample to analyze and work with varies widely across the different types of analysis, the different kind of sample matrices, the nature of the sample itself. And I just wanted to give a bit of context to that. So, for example, environmental samples, typically something like water samples or soils, etc. Typically, there will be a huge amount of material available. many milliliters of liquid available for a water sample, for example, or a large mass of soil which can be digested. So typically that kind of sample doesn't pose a challenge in terms of sample volume. Occasionally, you might come across a material that you have a limited amount of material to work with, but it's possibly less likely in environmental. Biological samples, that's possibly another example here. So samples taken from the body, something like a blood sample or a urine sample, those are common samples taken. Again, normally those are abundantly available. If you think of a blood sample for a moment, you might have, if you've just taken a blood sample from somebody in some sort of a volunteer suite in a hospital or something like that, or a hospital clinical environment, something like that, you may well have in a single vacutainer from the vacutainer sampling system, you might have 8 to 10 milliliters of blood to work with. If that's whole blood and that's what you're going to work with, fine, that could be diluted or digested, or even if you spin it down to get the plasma from it, you'll still have a lot of material to work with. So in that situation, sample volume and mass is typically not an issue. However, there are certain situations where that might not be quite true. So in the case of, if you were to take a blood sample from a baby or an infant, for example, then there is legislation in place which will limit the amount of sample volume you'll be able to take. So certain restrictions might come in that kind of situation where you wouldn't have as much to work with as you might do normally. Tissue biopsies, that's another example. That's the kind of thing where if a tissue biopsy is taken as a sample from somebody, that's not the kind of situation where a lot of material can typically be taken. The same with something like a spinal fluid sample. That's something where sample volume is not readily available in that case. So we're talking about something there, examples where you would have a limited amount of sample available, and that's forced on you as an analyst. Geological samples, a similar situation. In a lot of cases, if you did a whole rock digest, for example, you would still have a lot of material to work with. If you did a digest of a whole rock, if you're interested in trace element analysis generally, or isotope ratio work, you might have a lot of material to work with. However, if you were then interested in something like individual crystal grains, which is actually what I'm going to be coming to later in this presentation, something like a zircon or a monazite, you will have, for an individual crystal on an individual crystal basis, you will have a limited mass to work with. And in that limited mass, you might have a limited amount of actual analyte of interest. So there is a huge range in terms of samples, and there are situations where you might have to think quite carefully about how you'll introduce something if that sample is limited in its availability. So what are the implications of this? So a good place to start would be something like, if you had something where you had a low amount of physical sample available, if the analyte or analytes that you're interested in that sample is present at a low concentration, then for you to do a digest on something, or a dilution, or the first one then the other, that could ultimately end up in a reduction of the available analyte signal that you could get from that sample, and it might not be possible to detect it. So dilution and reduction of analyte signal is a real potential problem in this kind of situation. You might end up with a limitation in the analyte suite that you'd be able to work with. So you might be interested in a large analyte suite, a lot of isotopes and elements that you might be interested in measuring, but you might have to think carefully if you've got a limited amount of sample available, or not, which is what I'll get to. The number of replicate measurements that you want to make, again, same as the analyte suite. There might be time implications here in terms of measurement time in relation to sample volume. You might have to think about that. And then automating that whole process. If you've got a limited amount of sample volume, there might be physical challenges in actually being able to automate that. You know, simple things like getting a sample probe to your sample itself. So, you know, there may be limitations there in terms of automation. You might end up having to do something like a manual introduction, or not, as I will get to with the MVX system. But so there's a number of challenges here which will actually be quite familiar to a lot of people working in ICP laboratories. So there is something I'd like to mention on the idea of low sample volume. And often I've heard from talking to people in laboratories, or actually I've been in this position myself when I used to work in a laboratory, with a low sample mass or a low sample volume. A question is raised quite easily with that kind of sample of what can I do with this, or what data can I get from this? And those are legitimate questions, but I'd actually like to look at this slightly differently, and I'd like to turn this around to basically the following question, which is, what do I need? What do I want from this sample? So something more like, how many elements do I want from it? What is the data that I want to get out of this sample? Rather than what can I do with it, turn the question into what do I want from it? What do I want to get out of this? So that I sort of want to change the question to that. So anyway, I'll come back to that idea. And I want to move on to next the idea of just a brief slide on conventional sample introduction to ICPMS. Again, just to have some context here. So for a common approach for automating introduction to ICP optical or ICPMS instruments is automation that's driven by peristaltic pumps on an ICPMS system. So this is typically a situation like we have automation like this, our ASX500 series automation, like a 560 or a 280. This is the kind of automation where it's pitched to sample volumes at the sort of the low milliliter end up to say something like a 50 milliliter sample tube. That's the kind of automation where, you know, if you're doing waters analysis, fantastic, it works perfectly well. But when you get to the low volume end, you might have physical limitations of the sample probe. Can I get the tip of my sample probe to the sample for low sample volumes? And then also that sample may be introduced to an ICPMS instrument. It's being introduced by a peristaltic pump, and that flow rate from that pump is it's been determined by, you're not looking at it from the point of view of sort of like specific flow rate. It's determined by revolutions per minute on that pump. So it's speed of the pump in terms of revolutions per minute. And then there's also the question of things like, you know, how is my peristaltic pump tubing good for today's analysis? What kind of flow rate will I get from this? So for larger volumes, this is a perfectly great solution for automating this. But for the lower volumes, you might come into some difficulty, particularly if you start dropping down to less than a milliliter. So that might be an issue. Another conventional approach to automating this, a natural aspiration approach. So with a nebulizer, with a sample probe on the end of the nebulizer line, that probe is part of an automation system. So you're relying on natural aspiration, so the pull of the sample through the nebulizer according to the nebulizer gas flow. So that's how you're introducing your sample. this kind of automation is pitched for sample volumes of several hundred microliters up to maybe a couple of milliliters. This is the kind of situation where normally you would work with an excess of sample, and then you'd use this for introduction, and be wary of whether you create a vapor lock, that kind of thing. So that typically works very well for the high microliter level into the low milliliter level. So just as some context, as some background, really the thing I wanted to point out was the kinds of magnitudes of sample volumes here, and then also what's actually determining the flow. So in the case of a peristaltic pump, it's revolutions per minute turning of that pump, and then in terms of natural aspiration, it's your nebulizer gas flow. So the MVX system. Okay, so at this point, I wanted to return to the concept for today, really. So the idea of tailoring the sample introduction process to the volume. So what I wanted to refer to here, again, just talk back to specific sample volumes and specific introduction flow rates. And with that combination, and knowing what kind of data that we want to generate, we can generate sort of that maximum data. So is it a maximum amount of data? So is it a specific analyte suite we're interested in? Or is it something different, like precision, in the case of what we'll discuss today? And then, setting up that system, tailoring it to the introduction so that you overcome some of the challenges which you might have with conventional approaches to introduction. So the MVX system, what is it? What can it do? So I'll start here. The MVX, it's an advanced autosampler. Essentially, it's an autosampler system based on our ASX7000 series with additional syringe pumps and switching valve technology on there. So what can this system do? It's designed for the introduction of low or suboptimal sample volumes, in this case to ICPMS, but we can also use it for introduction to other kinds of analytical instrumentation as well. So normally you would use this system for the introduction of tens or hundreds of microliters of sample, or slightly higher. So if you're in a situation, what I call suboptimal is if you're in a situation where you don't quite have enough sample to operate with a peristaltic pump approach, or a natural aspiration approach, for example. You don't quite have enough sample to cover that full analyte suite that you're interested in. Then you could use this system to overcome that challenge. So approximately what I would suggest in terms of the sampling range, depending on the type of ICPMS that you are going to be working with, sampling range is about 5 microliters up to 1 milliliter in sample introduction range. Now, I say approximately. The smallest sample volume that I've introduced to a multi-collector instrument is 2 microliters. And as of yesterday, I introduced reproducibly 1 microliter aliquots into a chromatography system. So physically, which is capable of handling very, very low sample volumes for introduction. So that's volume of sample itself. What about flow rate? So we've actually got very specific control of how fast or slow a sample is introduced to your ICPMS via the nebulizer. So the range is down to 5 microliters per minute, which takes you into the total consumption range, all the way up to far exceeding any kind of flow rate that you would need for any other nebulizer for ICPMS. So I've put greater than 10 milliliters per minute here simply because it can go higher than that. So far beyond what you would need for ICPMS. So essentially it covers the full introduction range for any nebulizer that you might conceivably use for sample introduction. So in addition to that, we can configure the automation again to support the sample introduction. So there is capability with this system for sample homogenization. We can generate a degree of turbulence and mixing for your sample prior to the introduction process. So if you've got a sample where you've got a high level of TDS, for example, or anything where you might expect a degree of settling over the course of an analytical batch, you could factor that into your introduction process and make sure that you have a homogeneous sample being introduced. There's also an option for temperature control. So you can cool your samples down to 4 degrees centigrade or take them up to 40 degrees C, and depending on what your requirements are. So if you have concerns of sample matrix evaporation, for example, then you could cool the sample down to 4 degrees C, and essentially you're maintaining the integrity of your sample through the batch process. Similarly, if you have a capability, if you need to heat your samples, if there's any question of any kind of solidification, something close to with a solidification point close to room temperature, or if you need an incubation type temperature, you could raise the samples up to 40 degrees C. It's capable of septum piercing, so you could use septum piercing vials, or you could have sealed well plates that could work with that. And then, mentioning well plates, it's compatible with most 96 and 384 well plates. So up to 44 millimeters in height for a 96 well plate, so that the high capacity wells for those well plates. And then also it's got the ability to sample from a 384 well plate, which is requires a high level of accuracy and precision in the XYZ movements. You can also configure the rinsing processes for this, so you can have a greater or lesser extent of rinsing, so that you can make sure that you get down to baseline as fast as possible, even for analytes or matrices where there are more challenging situations, like analytes with no memory effects, or if you've got a matrix which is difficult to handle in terms of difficult to wash out. You know, we can configure the system for maximum efficacy. So, a quick tour of the hardware. So what we've got, I mentioned 384 well plates. Essentially, so this the central piece of automation. It's accurate and precise enough to sample from a 384 well plate. So I think that's probably the best measure of this, actually. If you're specifically interested in accuracy and precision down to a certain measure in terms of millimeters, please let me know and I can provide you that information. But it will accurately and precisely sample from a 384 well plate. Connected to this automation, we have 2 syringe pump modules. One of them is what we call the valve syringe module, and this is responsible for taking up a sample for sample introduction. So we've got a short half-height PSD4 syringe pump with a syringe at the bottom here, and then above that is a 6-port switching valve. So this small syringe will pull your sample up from a well plate well or a sample vial, and it will pull it onto the sample loop on this 6-port switching valve, ready for introduction. And because this is ICPMS and you want as clean a flow path as possible, we have a metal-free flow path from the sample probe all the way through to the nebulizer. So we use materials here, quartz, PEEK, CTFE, and PSA. The syringe and the syringe pump here on this pump, so that's a PFA syringe with PEEK fittings, and it's a CTFE syringe switching valve there. So on the other side of the unit, we've got a syringe pump. So just a syringe pump, it's a full height PSD6 syringe pump here, and this is essentially going to take the place of your peristaltic pump. So this will deliver an introduction flow rate that we decide, or the user decides, and it will push the sample off the sample loop on the 6-port switching valve to the nebulizer. Now, I say this is going to take the place of your peristaltic pump. There is only one use for the peristaltic pump when you're using this on your system, and that's for draining your spray chamber. So that's all that it's going to be used for. And similarly, as to the other side of the system, it's metal-free flow path, PFA syringe, PEEK fittings, and a CTFE syringe switching valve. So, how does it work? Essentially, I've described this already. So if you follow the blue and the green lines here, when we undertake analysis, we have a carrier flow from the syringe pump module, and it passes through the 6-port valve to the nebulizer. Whilst that's going on, we take up with the small syringe, we pull sample from the sample position up through that line onto the 6-port valve, so it sits there on the 6-port valve. We then switch the valve, and that sample is brought into this blue line flow. So if we switch that valve, the samples then, the colours have swapped over, so we're interested in the green line. So this green line, this syringe pump module is going to push the sample off the loop to the nebulizer. And whilst that's happening, the small syringe pump will do a back flush and clean the line ready for the next sample. So that's the introduction process. Now, I mentioned that we've got full control over the introduction flow rate, and it brings us to nebulizers. So we have the range of introduction flow rates to cover any kind of nebulization required for your application. And because we just simply connect the automation to the nebulizer with some fittings and ferrules, we're compatible with any kind of nebulizer you might have. So that's from all the way down to total consumption, down to the low 5 to 7 microliters per minute level, that kind of range, all the way up to anything that you would call standard automation. So 400, 500 microliters up to a milliliter per minute, and well beyond if you were so inclined. So any kind of nebulizer. So what I wanted to just finish this part of the presentation on was just to give you an idea of what that actually means in terms of sample. So we have control of flow rate. What does that do for us? So just as a quick example of this, what you're looking at here is some sample introduction profiles for a run-of-the-mill 1 part per billion multi-element standard. And what I've done here, I actually generated this data, and I've taken 100 microliters of sample of this multi-element standard just as an example, and I've introduced it through what you might call a standard 400 microliter per minute concentric nebulizer. So the typical kind of nebulizer that is common to most laboratories. It's sort of the off-the-shelf standard nebulizer provided with most ICP-based instrumentation. So nothing particularly special, like a standard nebulizer. So this 100 microliters of sample has been introduced at some different flow rates. So what I want to sort of make clear here is that we can stretch out what we've got to work with. So 100 microliters of sample isn't very much liquid to work with. And if we introduce that at something like a 200 microliter per minute introduction flow rate, which we've set, then we have here in the window of stable measurement, about 21 seconds of stable measurement time. After you've had your wash-in profile, stable measurement starts. You've got about 21 seconds and then it washes out. So that's great. But what if you've got a larger analyte suite and you need more measurement time? Well, you can reduce that flow rate. So the same volume of sample introduced at a lower flow rate, so 150 microliters per minute, and we go from 21 seconds and we add another 10. So we've got 31 seconds of stable measurement time, which is great, but we can keep stretching that out. And if you lower it again to 100 microliters per minute, you stretch out that time to 48 seconds, and you can keep going. You can just keep going and keep going. And the amount of measurement time that you want for your analyte suite or your general analysis from that sample volume. So we go to 75 microliters a minute and get to just over a minute. And then if you drop it down to 50 microliters a minute here, and then all of a sudden we've got a minute and 43 seconds, all from the same 100 microliter sample volume. So you really can make the most of your sample. Now, of course, if you stretch that out, something's got to give. You do give on the sensitivity that you've got there, and so your sensitivity might come down a little. But you've got the ability to work with this, and with most modern ICPMS instrumentation and the kind of sensitivity that's available from those instruments, that allows us to really make the most of the sample. So what I want to sort of finish on this particular slide with is that you can really start to make the most of low volumes. And that will actually give you a lot of advantages in terms of things like sample preparation. So you might be interested in a large analyte suite, and this will help you certainly get more measurement out of a large analyte suite, out of a small volume for a large analyte suite. But you might be interested in other things as well, such as analytical precision, which I'll get to. So, a geological example. So multi-collector ICPMS, this is where I wanted to get to today. So with some background on the MVX, how it operates, what it can do, we can work with low volumes and we can have real control over the introduction flow rate. And that I've given examples of 200 microliters a minute, 100 microliters a minute, 50 microliters a minute, but we can set that to anything. It could be 53, it could be 204. We're specifically setting what that introduction flow rate is. So, geological example then. So, I wanted to come back to what I mentioned before. So, single crystals, zircons, for example, in geological analysis with multi-collector ICPMS. So, really, I wanted to start with an example of a sample and an example of a measurement. So, in this case, uranium isotope measurement. So, for example, 235 uranium versus 238 uranium. So this is a required specific measurement in geological crystals. So zircons are a good example, monazites, etc., for accurate age determination. So this is part of aging studies, geochronology, for example. So in that kind of study and that kind of analytical measurement, the precision is a crucial aspect of this. It's a crucial part of isotope ratio analysis and high precision dating studies. So the analytical precision is crucial, because if the analytical precision is not as tight as it can be, that variability and precision is going to affect your data in terms of dating studies. So if you have a poorer precision on the analysis, that basically means that when it comes to dating studies, the time frames that you are referring to, that you're placing your samples within, also start to have variability in them, or a greater level of variability. Also, in samples of this kind, the overall mass of uranium that might be present in such a sample, i.e. the concentration, might be very low. So you might be looking at something like 1 to 3 nanograms of uranium in that kind of crystal sample. So in that kind of situation, if you do a digest and a dilution, then you might have challenges with the signal that you're looking to measure. So what do you do about that? I mean, there have been ways to go around this, digest multiple sample crystals. That's one way around this. But if there is any degree of heterogeneity between sample crystals, you're going to be bringing in more variability in this case. So sample volume, the final sample volume we'll come to, but again, there's challenges here with reconstitution, which brings us into sample preparation, which I'll get to next. So higher volumes might start to cause you a problem. So what do we do if we've got a zircon crystal? Well, in terms of sample preparation, individual zircon crystals, sample crystals, need to be digested for liquid analysis. So these crystals are typically digested in something called a BOM. So they're in a microcapsule in a BOM, and each sample crystal is digested in a very harsh chemical environment. So for each crystal, approximately 300 microliters of very strong hydrofluoric and nitric acid are used. You put these samples in that kind of situation at high temperature, so in this case 220 degrees C, for 3 days until these samples are digested down. So this is a very intensive process. It's a very aggressive chemical process and pressure and temperature process, but also it's intensive in terms of time. When the digest is complete, you then dry down each sample to residue, and then you reconstitute it into a specific sample volume that you then would introduce to your ICPMS. The key point I want to make here is, what volume do you reconstitute your sample into? So that's the key point, and that's what I'll get to here next. So the conventional approach to this, how it's typically done, is that you reconstitute that sample residue into about 1 to 1.5 milliliters of nitric acid. So, and what you do with that is you take that sample, that 1 to 1.5 mil volume of sample, and you introduce it via a self-aspirating nebulizer. That might be on its own, or it might be an automated approach to that. And then that sample goes through a desolvating nebulizer system. So, for example, our Aridus 3, where the sample is desolvated, the matrix is removed to keep the oxide level down, and then that sample, after passing through that, passes into your ICPMS for measurement. That's the standard approach, the conventional approach. Now with the MVX, we don't have to reconstitute the residue into such a high volume. So instead, we can use something a lot lower, we can reconstitute into something like 100 microliters, and then put it through a similar process. We introduce via the MVX, but at a flow rate we decide, through the desolvating nebulizer, again, to remove the matrix and the water, bring down the oxides, and then introduce into your ICPMS. But the difference here is that we're using a specific volume and we're using a specific flow rate. So for the example I'm about to give is 100 microliters of sample volume introduced at 70 microliters per minute. So as I've described, your reconstitution volumes for conventional 1 to 1.5 mil versus 100 microliters. So what does that mean for us? So, well, in this case, if you were to compare the two approaches with the same mass of uranium, if you put that same mass of uranium into a lower volume, so 100 microliters in this case, rather than 1 to 1.5 mil, then you will have a higher concentration per unit volume of uranium in the 100 microliter sample. And as you introduce that, or when you introduce that, your signal is going to be much higher in relation to the background. So your background signal. So something like this. So what you've got here is, if you follow the conventional approach and follow the red line here, you're going to have a lower signal to work with. And for the analytical precision that you want to achieve from this, you will have to introduce sample for a longer period of time. So hence the larger volume. So for a longer period of time, so it takes something of the order, I believe, for this kind of thing, 10 to 20 minutes of sample introduction, so that you've got the precision that you want. In the low volume approach with the MVX system, the signal is going to be much higher. And because the signal is that much higher against the background, you're using a lot less, your signal is going to be much better in terms of precision, and you're actually going to need to measure for much less time. So there is a time advantage here as well, which I'll come back to. So what does this mean for precision? So I've mentioned part of this already. A higher analytical signal allows for an improvement in the precision of this whole process. Higher signals mean that your precision you can either improve your precision, or you can start considering working with even less mass in your sample. So you can work with something like a zircon sample, which contains a much lower concentration, a much lower presence of the analyte that you're interested in this case, uranium. It also means that we now have access to some analytes which are present at such low concentrations, low presence in a zircon sample like that, that you've now got they're accessible now where they might not have been before to work at the precision that you want to work with. So an example of data for you. So this data is from our collaborators at the British Geological Survey, who will be mentioned in the acknowledgements. But I just wanted to give you sort of a real example of what this actually looks like. So what you're looking at here is a graph comparing amount of analyte, so uranium in this case, across the x-axis, versus precision of the 235 to 238 uranium ratio on the y. And what you've got here is what I want to compare here is the blue data points with the green data points. And if you go from right to left on the x-axis, so you go from high mass to low, if you start there, what you'll see at the 2 nanogram level is that for the blue data, that's our conventional approach. But for the same mass, if we use the MVX, our precision is a lot better. It's a lot tighter, and it comes in under the conventional level. So as you move down the mass scale from right to left on this x-axis, you'll see that the precision starts to worsen, if that's the right word, as you go down in mass. But for the low volume MVX approach, the precision is kept still always better than the conventional approach. But as you go down through to the 0.5 nanogram level, the precision that you get with the MVX system is on a par with the conventional approach at a much higher level. So you're looking at a four times improved approach there between the two. So what I'm saying here is that for the same mass, you have much better precision. But if you wanted to work with less samples that you know contain a lower presence of the analyte that you're interested in, you can maintain that precision that you would expect from the conventional approach, but at lower presence, lower mass levels. So in this case, uranium, lower nanogram levels. So this is what we've seen, and it doesn't just apply to uranium, it applies to other analytes, other isotope ratio measurements as well. So there are additional advantages as well, which I alluded to. So you are analyzing for a much shorter period of time compared to the conventional approach. It's up to 3 times faster on a sample per sample basis between wash-in and wash-out processes. So essentially, you're looking at a higher throughput. If there's a higher throughput, then this implies some degree of cost saving. So it's you're either looking at a situation where you are analyzing more samples in the same time period as you would for the conventional approach, or if you do have a finite number of samples, then essentially you'd be looking at saving argon and power, etc. Also, in the case of waste, you are wasting less sample because you are using all of the material that you are preparing in the first place. So essentially, you're using everything, so it's not quite total consumption, but not far away. So in the case of something like if you were going to be doing this kind of isotope ratio work in the nuclear industry, if you are generating a lot less waste, then that is certainly beneficial in terms of how to dispose of that waste that you would generate and the cost of doing so. So there is other advantages here other than just the analytical advantage in the first place. So just a few conclusions for this. So what I wanted to come back to immediately was sort of this concept at the outset, and asking that question: what do you want to achieve from the sample volume? So that question of I want to generate this kind of data, this analyte suite, or I want this precision from my sample, rather than looking at a sample of such low volume or low mass and saying, well, what can I do with this? So it's a new way of looking really at low volume or low mass samples. So as I've described, the MVX7100 microliter workstation system, you can use this to tailor your sample introduction process and address any challenges posed by limited sample mass or volume. So tailoring the introduction process to generate better quality data. The MVX system, it does, in the case of multi-collector ICPMS analysis for isotope ratio work, the MVX offers a real analytical advantage by being able to work with lower sample volumes. So you can go all the way back to your preparation steps and work out how best to get the best data via the MVX system into multi-collector ICPMS. And then there's the additional operating advantages that I described as well: the reduction of cost, improvement of throughput, improvement of disposal, etc., by generating less waste. So the key acknowledgements for this, I want to say a huge thank you to our collaborators at the British Geological Survey, so Matt Horstwood, Simon Tapster and Lewis Banks, all who have worked on the MVX system with multi-collector ICPMS for precision work on isotope ratio with uranium samples, and also other measures as well, lutetium, hafnium, etc. So they've done some great work, and this has all been looking very good. So thank you very much, all three of you. So I'd like to leave it there and thank everybody for your attention. And if you have any questions, please feel free to send them to my email address below. And thank you for your attention and for attending this webinar. Thank you very much. Thank you.